Okay, thank you to the organizer for having me here and to give me the opportunity to talk about another family of sources which have not been detected yet by Ligo and Kagura collaboration. I will talk about persistent sources of gravitational waves. Okay, I will probably skip this introductory slide because thanks to David that gave a nice update on the status. But just to let you know that I will focus on these two particular families of signals, which are continuous waves and stochastic gravitational wave background. As you can see, the main difference between these family of sources and transients is the duration, of course, but also the amplitude of these signals, which are orders of magnitude lower than those that have been detected so far. Okay, I will start by continuous waves. You can think about all those sources that are able to produce variation, okay, in an early periodic way. This means that the signal that we detect, that we should study at the detector, will have some modulations. These are both in amplitude and in frequency due to many effects, in particular the Doppler, because our detectors are on Earth, but we also have the response of the detector that should be taken into account. The typical sources that produce these type of signals are non-axisymmetric isolated neutron star, which have some, for example, a mountain on it, or neutron star in binary systems, in an accreting system, so with a lower companion, which is like in this figure here, where you have the neutron star spinning and is accumulating matter from the companion. But you also have more exotic objects like those that have been introduced by David, like boson clouds that are clamped around spinning black holes, but also dark photons. You can check those references here for more details about the sources and the type of searches we do. Okay, given that the type of sources we look for are quite wide, we also have to adapt our detection methods to the information we have about the source. In particular, the best method to look for these sources is the matched filter. But this can be only done if you know all the parameters of the system you are studying. In particular, for example, when we have known pulsars, where we know exactly all the ephemerides, so the timing solution of these spinning sources, we can use matched filter. In this case, we will use the most optimal method with the best sensitivity. And this is cheaper from a computational point of view because there is only, let's say, one template to probe. But when we expand, let's say, our parameter space, because we are not really, we don't really know exactly all the parameters, we go to more computationally expensive searches, and which are also less sensitive, like, for instance, blind surveys. Okay. Okay, I will start now showing you some of the latest results using the O3 data. For the case of targeted, like for known pulsar, in this search we have been targeting 236 known pulsars. Of course, all the information are provided by electromagnetic partners. And as you can see here, we have some famous, let's say, pulsars, which are Crab and Vela pulsars. And you can see that we are starting to probe energies, like in terms of strain, which are well below what we call the spin down limit. So basically, when you have a source which is spinning and you assume that the whole energy is released in terms of gravitational waves, you can put these constraints here, these triangulars here. But then when you go to study exactly the quantity of energy they are emitting, you realize that you are not able to detect those signals, and this means basically that the stars is releasing energy in gravitational waves at a percentage smaller than 100%, basically. Okay, then we have another category of searches, which are those for sky regions, which can be interesting, like the galactic center. We know that in the galactic center there is a huge quantity of potential targets of this type of sources, and that's why we perform those searches pointing to the galactic center. In this case, we arrive to values of the so-called upper limits in terms of the strain, which are of the order 10 to the minus 26. Do you remember that I told you that so these sources are emitting with a strain which is of this order, or even lower, because this is like the one of the minimum, let's say, values we reach with our detectors, with current detectors, but still we didn't have any detection yet. So it basically means that the strain of this, of this source is really low. Okay, then we also do searches for supernova remnants. Of course, also here we need to have electromagnetic counterparts information. I need to go very fast. We can also do searches for low mass X-ray binaries. We reach limits of 4 times 10 to the minus 26 for Scopus X1. We are basically probing the so-called torque balance limit. And we also have all-sky surveys for isolated neutron star, boson clouds, and dark photon that are being introduced by David. Let's pass now to the stochastic gravitational wave background. We have two main family of sources which are able to generate those stochastic background. One is the astrophysical origin, so basically the collection of all the compact binary coalescence and more signals, but also we have the cosmological origin, basically vacuum fluctuation, cosmic streams, primordial black holes, and other nonlinear phenomena. All these sources have in common the fact that I always searched with cross-correlation methods. So, but of course, the model of the spectral shape is a little bit different according to the source we are analyzing. Some results about the isotropic of research. So basically, you can see that the main limits that I put in those searches is in terms of this density, for stochastic searches, and you can, according to the population you are analyzing, you can put this limit here. You can also put all this limit together, and you will have that basically the prospects are that for future detectors upgrades, we will start be able to probe this astrophysical background, because this is astrophysical background, so from CBC searches. There is also a family of anisotropic searches, and also here we have limits. In this search in particular, there are being used three methods, one targeting a particular family of sources, like broadband, extended sources, or also continuous, like more standard continuous wave sources, like the galactic center again, Scopus X1, and supernova remnants. And I think I finished the time, and we are like, this type of searches is a little bit more difficult, I would say, compared to compact binary coalescent signals. But we are quite sure that we are starting to probe more and more interesting, let's say, energies in terms of gravitational waves. We are working towards the increase of the sensitivity of those pipelines in order to have these discoveries. And the outcome, when we will have, if we will have a detection, might have to constrain the physical neutron star matter, because we are able to translate our limits into the deformation of a neutron star, the degree of deformation of a neutron star in terms of ellipticity or R modes, saying something about the B fields, like the magnetic fields in low mass X-ray binaries, and of course we can also understand neutron star population a little bit better. For stochastic searches, it's true that those searches are really model dependent, so we cannot really extrapolate a general conclusion, but all the conclusions we will have are all model dependent. But in general, we can start to say something about the history of the universe, and for sure we will be able to probe CBC events rates, so compact binary coalescence events rates. There are also a bunch of searches for dark matter candidates, as you have seen, both via gravitational wave emission through, for instance, boson clouds, or direct detection in the case of dark photons. And I think it's done.
Hello. I think we have a question about the background. in the case of neutron star, how is the power carried away by gravitational wave compared with the spin down luminosity of neutron star?
In the case of neutron star?
Yeah, the neutron star usually we can measure the spin down, something called spin down luminosity.
Yes.
Yeah, how is the gravitational wave luminosity compared with the spin down luminosity?
The gravitational wave compared to?
Compared with the spin down luminosity. Your gravitational wave will have some power, right?
Yeah.
How is this rate compared with the spin down luminosity?
Yeah, okay, so what? Okay, so we can. So if you assume there is a spinning neutron star, we know that the channel of emission might be multiples. Okay, it can be fully electromagnetic, it can be electromagnetical, gravitational, and so on and so forth. So basically, this triangle here tells you, tells you that the star is emitting fully in gravitational waves. So this is the maximum amount that the star can emit in gravitational waves. But it doesn't tell you that it should emit at this energy. Indeed, what we see, these are the stars are the results we have from searches. And so basically we didn't observe those yet. So it means that basically for the Vela pulsar, which is here, we can say that, for instance, for the Campus Vela pulsar, we have so far, we know that for sure the gravitational wave amount of energy should be 100 times lower than the spin down limit. So, but it can be even lower. We don't know. The main reason why we don't know this is that let's say the energy in releasing gravitational waves depend on the deformation of the star. And the deformation of the star depends on the equational state of the star. And we have this very little parameter which is called ellipticity that I couldn't really explain, I'm sorry, that tells you the degree of deformation of your star. And the degree of deformation of the star, the quantity we are reaching are of this value. And for targeted searches of the order of 10 to minus 8.
Thanks a lot. Do we have any other quick question? Well, if I may, so I think you were trying to mention here that the sensitivity was for some sources were starting to be enough to be able to see them. So is there a potentiality that there is a detection in O4?
Yeah, the thing is, you can basically, from this plot, you can start seeing that if you consider the non-pulsar, okay, those whose searches should be the most sensitive one, we are starting to go to probe a bigger number of sources, because so far we are starting to, so the so-called spin down limit has been beaten only by a fraction of all the pulsars we have been analyzing. Like in this case, only 23 out of the 236 so we have been able to beat this limit only for 23. But it means that in O4, when this curve basically will go lower, we will start to add much more sources to this list of sources that beat this limit. So technically, yes, the answer is yes, but I cannot put my hands on fire because we have still the uncertainty on the parameter I told you before, which is the ellipticity. And when matter enters in this discussion, it's really difficult to know exactly what's inside a neutron star, because then you have to add all the microphysics and all the equational states. So there are ellipticities which have been so for some sources, for a particular condition with the B field and so on and so forth, it has been also values of 10 to the minus 9 are still sustainable, which are really little. So maybe.
Okay, I'm looking forward to seeing if it's a limit or not. Okay, let's move on to the last with this.